I'm going to try to go over the nature of truth trees in this lecture. Basically, this is a way of testing the semantic commitments of the sentences that you start with. Um, so I make use of this notion of semantic commitment here. Suppose we start with the sentence A and B. Well, that obviously commits us to A, and it obviously commits us to B. Okay? And the idea of the tree is, though we start with complex sentences, we try to break them down into their simpler components to see what our commitments are. And in fact, we try to, as I say here, reduce the complexity of our starting sentences down to the atomic bits and to negations of atomic bits. Okay? And if you can do that, then you can sort of see much more clearly what your commitments are. Now, if we're going to reduce all of these complex sentences down, that means that for any sort of sentence form, we've got a distinct rule of decomposition for each of those. Okay. So what we just saw is already the rule for and. The sentence A and B commits us to A and to B. So we just decompose it in that way by writing A and B on the same line underneath our conjunction. Okay. And all this says is that if A and B is true, well, then each of these conjuncts has to be true as well. Okay, suppose we have the negation of a conjunction, not A and B. Well, in this case, we know that one of these things, A and B, is false, but we don't know which. Okay, and this is when the sort of case when we need to have a branching rule. Okay, so we have not A and not B here, but they're not written all in the same line. They're written in this branching way, and the idea is what this is supposed to represent is, well, either not A is true or not B is true. We don't know which. Okay? So that's the rule for decomposing a negated conjunction. Now, you might be wondering at this point, well, what does this mean? What are we doing? How does this help us show what we want to show? Suppose, for example, we wanted to show that A and B and not A and B really are incompatible. Okay. Well, if we put them on the same tree, then we ought to be able to show this incompatibility by using these rules of decomposition. So how does that work? Let's illustrate that. Here's our two sentences, A and B, and the negation of A and B. We decompose the first sentence first, so we write down A and then B, and then we write down the decomposition of this sentence. So we get this branching pattern, not A and not B. And now here's the idea. We can think of each branch as a kind of possible world. Okay? And if we look here on the left side, we see that we've got not A, but also A. And similarly, if we look on the right branch, we see that we've got not B and also B. Okay? Well, wherever we have that kind of incompatibility, that kind of contradiction, we'll just place an X here to close off the branch. Right? And because both of these branches close, and we're done decomposing our sentences, this tree as a whole, we say, is closed. And when a tree closes, that just is another way of saying that the assumptions with which we began are in fact incompatible. Right? It cannot be that A and B is true and that not A and B is true. Right? And this tree is a kind of graphical picture of that incompatibility. Right? Because if both of these sentences were true, per impossibile, right, well, that would mean either that both A and not A would be true, but that can't be right, or that B and not B would both be right, but that can't be right either. Okay? And that's exactly what it is to have incompatible sentences. Okay? The rules for or are sort of mirror images of the rules for and. So if we have an ordinary disjunction, then of course, of the two disjuncts A and B, well, we know that one of them has to be true, but we don't know which. So we write it in this branching way again. A on one side and B on the other. The rule for the negated disjunction, right, if we have a sentence like this, not A or B, that's a different story, because in that case we know, in fact, that this disjunction can't be false unless both disjuncts are false. Right? So we decompose this by writing not A and not B on the same line. Okay? Much like the way we wrote A and B on the same line as A and B when decomposing A and B. The rules for the horseshoe and for the negated horseshoe make more sense if you remember that the sentence A horseshoe B is in fact equivalent to not A or B. If you haven't seen this before, I've got a truth table here that illustrates that. Right? When is A horseshoe B false? Only when A is true and B is false. Okay, which of course is also the condition, the unique condition under which not A or B is false. Right? We would need to have A true and B false. Okay, and so unsurprisingly, given that that equivalence, the decomposition rule for the horseshoe looks like this: not A on one branch and B on the second branch. Right? One of these two things must be true, but we don't know which. The negated disjunction, the negated horseshoe has a rule like this. If we know that A horseshoe B is false, well, again, that can only be if A is true and B is false. That is, if A is true and not B is true. Okay. Now, there's one more rule we need, and that's a rule to take care of multiple negations. Okay. So if we have a sentence with double negation, this is pretty straightforward, then we can remove those. Okay. So notice this rule allows us to reduce a sentence with 2 negations down to 0. It also would allow us to reduce a sentence with 4 negations down to 2, or 8 negations down to 6, etc., etc. Okay. With any luck, we won't come across such gigantic strings of negations, but if we ever do, we can use this rule to get rid of them 2 at a time. Okay, let's talk a bit about the applications of these trees. Well, the biggest application really is, we've sort of gone over this already, is to show when you've got an inconsistent set of premises. Right? Because to show that a set of premises is inconsistent, all you have to do is to show that the tree in question closes. Right? And if there are multiple branches, then each, for that tree to close, is for each of those branches to close. Okay. So for example, let's start with a simple one: P horseshoe Q, P, and not Q. We'll start with those at the top of the tree. And clearly this ought to be inconsistent, because we know that if we have both P horseshoe Q and P, we must have Q, which is plainly incompatible with not Q. Okay, so we should certainly expect this tree to close. Let's see how it goes. There's really only one sentence to decompose, namely this horseshoe sentence. Okay, and when we do that, we get not P on one side and Q on the other branch. Now let's look at those two branches, right? Well, on one branch we have not P and P. That can't be, so we can close that branch immediately. But on the right branch we have Q and not Q. That can't be either. Okay, so we can close those branches, and in fact the tree as a whole is closed. And again, what that shows is that this starting bunch of assumptions is inconsistent. Okay. Now, of course, that example was really just a sort of teaching example, because you can tell just by looking at the set that, of course, this is going to be inconsistent. But what's nice about the tree method is that you can keep using these mechanical rules. It works the same way, even in much more complex cases, like, say, this. Okay. Here again is a set of 3 sentences, and again they are inconsistent, but that's probably not at all clear to you. But one way to check is with trees. Okay. Now, since these sentences are complex, we have to think a bit about how to decompose them. What sort of sentence is this, for example, right? Well, there's a bunch of negation symbols and there's a disjunction symbol, but clearly the main connective is this not that's out in front. Right? So I'm going to stop here for now, and we'll pick up here in the next lecture.